Hey everyone, welcome back to our channel and the series about data engineering and data science within Microsoft Fabric. Today, Amir joins us to continue the discussion about Fabric data science samples, and will present one more detailed demo. So to kick things off, Amir, thank you so much for accepting the invitation.
My pleasure, Estera, and thank you again for having me for the third time. I'm super excited today to walk you through another sample. As you know, in Microsoft Fabric and data science, we try to cover different data science samples that actually cover different paradigms of machine learning, which is like regression, classification, and time series prediction. In this case, and today I'm actually going to walk you through another sample, which is actually about classification. It's a machine failure, which we try to actually build more of a systematic approach to kind of proactively predict which machine in a line of machines would actually fail, and then like maybe take predictive actions to avoid doing that. This actually also falls into the area of anomaly detection, which is very common in machine learning and data science. With that, I'm excited to kickstart the demo.
Yeah, can't wait, as we got the great previews for doing the episodes about the demo, because just to emphasize, if you have a trial account and trial is free, you can run those examples. And we want to show you how easy it is to start your journey with Fabric, especially here with data science, as you don't need to configure an execution engine, an Python virtual environment to run the experiments. It's ready for use, and just by clicking one button, you can start building some great models. So please check the previous video when Amir presented both churn analysis and also forecasting and prediction scenarios. And let's jump to today's demo. Can't wait to see it.
In this notebook, we will walk you through the process to show how to create, evaluate, and score a machine fault detection model. The scenario is to use machine learning to have a more systematic approach to fault diagnosis in order to proactively identify issues and take actions. Specifically, our aim is to predict whether a machine would experience a failure based on specific features such as process temperature, rotational speed, etc. Before we proceed, I need to remind that we first need to add a lakehouse to this notebook, which we have already done. If we click here, we can see that the lakehouse is added, and the name is machine failure _LH. So the first step is to actually install custom libraries. When developing a machine learning model or even performing ad hoc data analysis, we may need to quickly install a custom library, which is in this case is imbalearn, for any Apache Spark session. You might ask, why do we need to install a custom library? I will explain that in our next steps. But in order to install a library, you usually have two choices. First, you can use the inline installation capabilities, such as pip or conda, to quickly get started with new libraries. But bear in mind that if you use inline installation capabilities, it would only install the custom library in your current notebook and not in your workspace. Alternatively, you can also create an environment and then install custom libraries from public resources, or even upload your own custom libraries. In this notebook, you need to install imbalearn, which is also known as imbalanced learn, which is a library for a synthetic minority oversampling technique, or known as a smooth. And we will proceed with the in-code installation capabilities such as pip install in order to install this library. So you can see that using pip install, we have been already able to install imbalearn. Now, the second step is actually to load the data and then get to know how our data look like. So our data consists of 10,000 data points about manufacturing. It basically simulates logging of a manufacturing machine's parameters as a function of time, and it's represented by a number of different features, which includes a unique identifier, which is known as UID, and it ranges from 1 to 10,000, product ID, air temperature, the process temperature in Kelvin, the rotational speed, the Turk, and the tool wear, and machine failure label. Note that in this case, if at least one of the above failure modes is true, then the process would fail. So this is some general information about our data sets. Now let's actually dig deeper in how our data set looks like. First of all, we have our dataset uploaded in the Azure Blob Storage. So using this tool, we are actually gonna download the data from our Azure Blob Storage, and then we're gonna actually upload it to our Lakehouse, which is already done here. And then it's always a good practice to record the time it takes to run the notebook. And here we are actually running the time it takes we are recording the time that it takes to run the notebook. So once we have downloaded the data from our Azure Blob Storage and uploaded to our Lakehouse, now we can actually read our data from our Lakehouse, and this is how it looks like. So you can see that our dataset contains a number of features and a target variable such as UDI, product ID, type, air temperature, process temperature, rotational speed, torque, tool viewer, target, and failure type. So you can see here that some of our features, we see in the naming, there's a space. So in order to kind of simplify the Spark processing, we're going to actually replace the spacing with underline, which is happening here. And now we are actually saving this as a new table to our Lakehouse. So you can see here that now our features, instead of having a spacing, we have an underline here, which is usually easier for Spark processing. And as I mentioned, we're going to now save this new data set with modified names for our features to our Lakehouse. So we got our data from our Azure Blob Storage. We kind of did some minimal processing, and now we have set in our Lakehouse. But actually now let's do some exploratory data analysis and pre-process the data for our next following step, which will be actually training machine learning model. Usually when we're dealing with Spark data frames, we also wanted to actually perform some visualization and data processing. So let's first actually, it's easier for pre-processing and also visualization to deal with like Pandas data frame. So it's sometimes a good practice to convert a Spark data frame to a Pandas data frame, which we're going to do that. So here we can see that we're converting we first read our data from our Lakehouse, and then we actually convert it from a Spark data frame to a Pandas data frame. And we're also gonna drop some columns because we realize that features such as UDI or product ID, they do not have much like a predictive nature, so they may not actually have valuable information for us, so we're gonna actually drop them. We also realize that our target feature, which is known as target, is not descriptive enough in terms of naming, so we're actually going to change the name to isFail. And now you can see that the target attribute has changed from the name target to isFail, which is more descriptive and easier to detect. And we have also realized that we have dropped these two features as UDI and product ID. For our feature type, we kind of realized that it has a strings as the values as M, L, and H, which is also mentioned in our first description here as LMH. We're going to also convert those and map them to numerical values of 0, 1, and 2. And the other thing is that we're going to do is we also convert a specific columns of data sets to floats and integers. So you can see that for air temperature Kelvin, for the process temperature, rotational speed, torque, and tool viewer, we actually convert them to different float types. And as I mentioned, we also make sure that they convert the target column to integer. And we're also going to map the values in the type column from L, M, and H to numerical values. So L is represented by 0, M is represented by 1, and H is represented by 2. So we have done some preliminary data analysis, kind of cleaning our data, converting some sort of like categorical values in a feature to numerical. And now actually let's start exploring our data. For first step, we are actually gonna do a correlation matrix, and we're gonna actually plot a heat map to kind of understand what is the relationship between for example, our target attribute and also different features. Plotting the correlation matrix and the heat map, we can actually realize that air temperature, process temperature, rotational speed, torque, and tool wear actually have the highest correlation with the isFail variable. And isFail variable, if you remember, is the target that we are actually trying to predict whether a machine would actually fail or not. And as you can see that this color bar shows like the extent of the correlation. So We have plotted the heat map and the correlation matrix, so we have got a sense of how different features are correlated with our target variable, but it also helps us to kind of also plot the histogram of different features. Specifically, we want to kind of plot the histogram, which kind of shows a distribution for columns such as air temperature, process temperature, rotational speed, torque, and tool wear. So we're going to show this, and what we actually realize is that these features, we don't see much sparsity, and we actually see some sort of a continuation in the distribution of the values for these features, which kind of give a sense that maybe these features are well positioned in terms of training a machine learning model. Now, so we have kind of so far looked into different attributes, but also let's look at our actually target variable, which is fail, which is like determining whether a machine would actually have failed or not. Is if you look at here, we are going to actually plot the number of counts for no failure in each failure type. So we have different failure types, right? Whether the failure is caused by tool wear, power failure, random failures, and all of that. But overall, we are seeing that from 10,000 data points that we have, over 9,600, there is no failure, and only around like 300 failures we have had, regardless of the source of the failure, whether it is overstrain or any of these, but in combination there's only like 339 failures. So this gives a sense that actually our data set is imbalanced, because out of 10,000 data points or samples, we have 9,652 of no failure and only like 339 of failures. And if you remember at the beginning of this notebook, we actually installed a custom library imbalanced, which we talked about the smooth, and that is the reason. So when you actually have an imbalanced data set, it is better to kind of use some techniques to kind of balance your data set to actually help your machine learning training step, and that's what we're going to do here. So first, let's actually separate our features. So again, our label is failure, which is the variable that we're going to predict, and also we have the features. These are the features that we have. So let's actually like now separate or split our data set into training and test data sets. So we have done here, we have separated our data set to train and test. You can see X train, X test, Y train, and Y test. What I'm going to do, I'm going to actually again save my training and test data sets to separate tables into my lakehouse. So for future use, I can actually read them from my lakehouse. And as I mentioned, we just noticed that our data set is imbalanced. We have a minority class, which is non-failure. It's only like around 300 samples, and we have a majority class, which is non-failure, which is like around 9,600. So what we're gonna do, we're gonna actually oversample, and for that we're gonna use a smooth, which is actually a widely used oversampling technique that generates synthetic samples. It generates examples for minority class, which in which case here is the failure class. And based on based on the distance between the data points using Euclidean distance. And we're also going to use actually MLflow to automatically log and track the whole process that we're using in this notebook. So we have X-train and X-test, and I need to mention this as it's a very important point that you're only going to apply a smooth to your training data set. The test data set should be considered as an unseen data set that you're going to set aside. So you're going to only apply the smooth to balance your training data set. So you're actually going to apply smooth to your train data. And the point that I also need to re-emphasize is that here, when we actually pip install imbalearn is actually the custom library we use to actually import the smooth. So if we go here, you realize that here from imbalearn that we just installed at the beginning of this notebook, we're gonna actually import smooth, and we're gonna use a smooth to actually balance our data set. Now, once we do that, now let's take a look at our new training data, and we can see that we actually have more or less the same number of data points in both majority class and minority class, and that this would actually help our machine learning step. So far we actually got our data, we kind of visualized our data, and we realized that we have an imbalanced data set, and we use a custom library called the smooth in order to actually balance our data set, and that's what we are seeing here. Now, The next step is actually train a machine learning model and evaluate the performance. We're going to try three different machine learning models known as random forest classifier, logistic regression classifier, and XGBoost classifier. And we're going to train all of them and then see how they perform. And as I mentioned, we're going to use MLflow. MLflow is already embedded. So we're going to automatically log all of the training parameters, the training the metrics that we want to evaluate our machine learning model. So later on, we can actually refer to our log models and actually see which model has performed the best, which model has performed the worst, and then actually pick the best model. So let's start with the random forest classifier. Again, as you can see, we have MLflow, which is automatically logging all the parameters and metrics for the model. And then we are going to train it, and then we actually are also going to have different metrics such as like F1 accuracy, F1 score, recall, the accuracy, and then we're going to also do it for the test data as well as the training data. So we can see that, and then you can see that as we have done that, everything is kind of actually logged in here. We also gonna do the same for logistic regression. You can see that we are again logging the F1, the accuracy, the recall, both for the training as well as we can also see that we are doing it for the F1 accuracy and recall for the test data, because while you can have great performance on your training data, which you actually use to train your model, you actually want to evaluate your model on your test data to actually see how it performs, because test data is unseen data. So it's actually very critical and important that you actually have a good performance on your test data. Showing a great performance on your training data is great, but it's not enough. So you also want to evaluate on your test data because that's unseen data. So we also do it for logistic regression. And finally, we're also going to train a model on an XGBoost classifier. Again, as you can see, we use MLflow to log all of the training parameters and the metrics, all of that. And we're also going to log the classification metrics such as the F1 score, the accuracy, the recall for the training data, as well as for the test data. And again, everything is going to log it here. So now we have trained three different models. We have logged all the parameters and the metrics. And next step is for us to actually see which model to select and which one is actually performing the best. In order to achieve that, you actually have two different approach. One is through UI. You can actually go to your workspace and then like select models, and then you can see different models. You can see here XGBoost, random forest, and logistic regression. And as I mentioned, you can actually track and see the performance for all of these models. Even if you tried different versions of the same model, you can see everything is automatically logged. So you can actually see, for example, the F1 score, the accuracy, the recall for the training data and tests. Whatever you have decided to kind of log, it's going to be showing up in your model under your workspace, and that's easily allow you to select the best model. Alternatively, you can actually also kind of use this script to actually look at the performance of different models. So you can see here we have different baseline metrics, and then we have it for random forest, we also have it for logistic regression, and we also have it for XGBoost. And what we realize is that while XGBoost actually shows the best results and best performance on the training set, it actually kind of performs relatively poorly on the test data set, which kind of shows that overfitting means that during the training, it actually overfits to your training data. So it also kind of learns all the noise and sort of all those like peculiarity in your training data, and it's failing to generalize to the test data, which is kind of unseen data. On the other hand, logistic regression seems to perform poor on both the training and test data, and random forest actually strikes a good balance between a good performance on the training data and the test data. So we're going to actually select random forest as the best model. So then we're going to actually kind of use the predict feature to actually kind of make a prediction using random forest and have the prediction results. Once we do that, the final step in every machine learning or data science project is how can actually kind of leverage the new predictions. So you have trained a model, you have selected the best performing model, and then you have actually made the predictions, but how can you get insight? And that's where actually once you use predict to make predictions, you can actually save the prediction results into a lakehouse, and then you can actually import it to Power BI to actually create Power BI dashboard. And then that's where you can actually kind of realize that what business insights you can get. Like you, for instance, you can see that, okay, based on the observations, the number of failures have dropped to like 250. That means like 12.6%. And then you can realize what next steps you could take to actually further minimize the number of failures that would happen. And again, what else it shows? It shows that, for example, the tool wear and torque create a noticeably boundary between failed and unfailed cases, and that gives you some insight at what you could possibly do to kind of even further avoid that. And finally, as I mentioned, it's always a good practice to kind of save the entire time that it takes to run the notebook. And you can see it only took us like around 117 seconds. So this notebook actually kind of walks you through the whole process to kind of do fault diagnosis and then learn how we could do proactive actions to minimize the number of failures.
Great demo. I mean, I want to emphasize the great example of using multiple features, because like we saw you installed the libraries through pip, through conda. Also using the predict method that some time ago Urin has presented also in the Espresso video. I'm wondering, is this demo targeting a specific, like industry specific scenarios, or it's kind of reusable? Because here machine failures, it's well-known scenario for our retail customers and like for different companies which are in that business. But can we somehow extrapolate it, reuse it in different scenarios?
Of course, sure. First of all, thanks for bringing up the point about we are showcasing different features of data science in Microsoft Fabric. As you mentioned, in all of the samples, and specifically in this sample, we try to actually showcase how to leverage different features in Microsoft Fabric, from how you can actually install some custom libraries using pip or conda, or like, you know, how to log different experiments and machine learning models that you train, as well as like using predict features. So we're trying to showcase that. So if you want to use it for your own use case, you can actually follow the steps we have done. Now, to answer your second question, well, while this sample is actually showcasing in a sort of like a line of machines, how to predict which machine would fail, you can easily like extend it to any scenario where you want to build a systematic approach to predict which element would actually fail, and like, you know, predict some sort of anomaly, and then like leverage that information from your learnings to kind of make some predictive actions to kind of avoid that. So yeah, for sure, you can extend this to your use case. The samples is just basically a way for you to walk you through how you can leverage Microsoft Fabric data science artifact, while also very easily extendable to many different scenarios and different industries.
Looks great. Thank you so much for today. Thank you all for watching us. And remember, as always, if you enjoyed this episode, leave the comment, leave the suggestion for the next episodes, for the next samples as well. Hit the like button, subscribe the current channel. And until the next time, happy discovering Fabric data science samples, especially machine failure and in general predictions. And see you next time. Thank you.